Okay, so first of all, what I want to do is cover section 11.3. And as I said, the 9 to 21 odd, that's your homework from this section. Now, by now you should know what is a series and what is a sequence. And we looked at geometric series in section 11.2, and we know exactly what is a geometric series and when does a geometric series converge and when does it not converge. For what? So the geometric series converges if the common ratio is between -1 and 1. Otherwise, it doesn't converge. It is divergent. And we also know when it converges, it has a sum, and we have a formula for the sum, right? The exact sum of the series. However, the exact sum of a series is something that you cannot always find. Okay? So usually, given a series, you actually estimate the series. If a series is convergent, you estimate the series, the sum of the series, by adding, say, first 100 or 1,000 terms. Okay? Now, a lot of the times it is important to know whether a given series is convergent or divergent. Okay? You don't need to know the exact sum. You need to know whether the series is convergent or divergent. And section 11.3 is going to give us a test whether a given series is divergent or convergent. Now, 11.3, 11.4, 11.5, 11.6, all these sections will give you different tests for convergence. Okay? And things get complicated because it's not, these are all very simple ideas, but there are a couple of different tests for convergence, and the hard part is to remember all the tests, first of all, and then when to use which test. And that's also something that you cannot, even if you understand everything I say, if you don't do the problems, you won't be able to understand how to apply them. Okay? So make sure that the homeworks are done on time. So here's, I'm going to start with an example. Let's say I have the series, the sum n going from 1 to infinity of 1 over n squared. So what's the series? It's 1 plus 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, plus da 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 da. If I look at the partial sums, so in this table what I have is I have the values of n and the corresponding partial sums. So S5, remember, is the sum of the first 5 terms. S10, that's the sum of the first 10 terms. S50, that's the sum of the first 50 terms, and so on. Now if you look at the partial sums, it seems like the partial sums are converging to something like 1.6. Would you say that? However, the problem for this series is that we can remember in the case of the geometric series, we were able to come up with a formula for Sn, right? We were able to come up with a closed form formula for the nth partial sum in the case of the geometric series. And then we took the limit to come up with the sum. But for this series, you cannot come up with a closed form formula for the nth partial sum. And because we cannot come up with that, we cannot just take the limit of the nth partial sum to decide whether the series is convergent. Am I making sense? So what should we do? Well, first of all, what you want to realize is this series that I have is the following. if I take the function, let me write up here actually. If I take the function, my son was making all drawings yesterday and I have them there. So here's what I'm saying. Let's say I have the function f of x, and the function f of x is 1 over x squared, and let's consider this function for x larger than 0. So what is f of n then? F of n is exactly 1 over n squared, right? Is that right? So if I look at the sum, so remember we are looking at the series n going from 1 to infinity of 1 over n squared, and then I could say that that's the same as what? This is basically sum of f of n, right? The sum of f of n. So this series, the terms are related to the function f, right? So here's how we can use the fact that the function f is related. So notice the blue curve that I have here, that's the graph of 1 over x squared. And what I want to show is that the series that we have, that's actually the sum of the areas of the rectangles I do. Okay? Let's see how. I have the graph of 1 over x squared. Everybody's okay with that? Okay? What I did is that the interval from 0 to infinity, I divided that into sub-intervals. 0 to 1, 1 to 2, 2 to 3, okay, and so on. On each, so what's the width of each subinterval? 1. On each subinterval, then I am drawing a rectangle where the height of the rectangle is the height of the curve at the right-hand point. Did that make sense? The height of each rectangle is the height of the curve at the right-hand point. Now, what's the area of the first rectangle? You realize that the area is basically the same as the height of the rectangle, right? Because the width is 1. What's the area of the second rectangle? 1 over 2 squared. Third one, 1 over 3 squared. Fourth one, 1 over 4 squared, and so on, right? So if you add them up, what do you get? You get exactly this series, right? This series, the sum here, it represents the total area of these rectangles. You guys agree with that? Now, what I'm going to do here now is I'm going to separate the first term and just concentrate on the remaining terms. So separate the first term, look at the remaining terms. So remaining terms means the remaining terms here, they give you the total area of the rectangles to the right of 1, right? So from this point, the series represents the total area of the rectangles to the right of 1. These rectangles here. Would I be correct if I say that the total area of the rectangles to the right of 1 is smaller than the area below the curve to the right of 1? You guys okay? The total area of the rectangles to the right of 1 is less than the area below the curve to the right of 1. Area below this curve to the right of 1 is bigger than the total area of the rectangles. But what is the area to the right of 1 below the curve? That's given by what? That's given by the integral from 1 to infinity of the function 1 over x squared, right? So the integral 1 to infinity 1 over x squared dx, that integral gives you the area below the curve to the right of 1, right? So then I could say the terms, the series after the first term would be less than this integral, but that integral we computed last time, right? And we computed that to be what? Last time we computed that integral to be 1. Exactly 1. It was exactly 1. So then I could say that the series that I have here is less than 2, right? Did that make sense? Everybody, did that make sense? So can I say now then, if I look at the nth partial sum, right? The nth partial sum is 1 plus 1 over 2 squared plus 1 over 3 squared plus plus 1 over n squared, right? That's the nth partial sum. If the entire sum here is less than 2, then every single nth partial sum for any n, Sn is less than 2, right? And is it also clear that Sn is an increasing sequence? Because all the terms are positive terms, right? So if you add more and more, you are increasing the sum, right? So Sn is an increasing sequence. Sn plus 1, the next value of Sn is always bigger than the previous. And it is bounded about, right? So I have the sequence of partial sums is increasing, but it's bounded about. The sequence of partial sums is increasing, bounded about. Then we know that it has a limit, right? Because in 11.1, I think that's where we said that if you have an increasing sequence which is bounded above, then it has a limit, right? So Sn has a limit. Sn has a limit. Are we okay with that? So that tells you that the series is convergent. Did that make sense? Let's look at a new example. Now look at the series where the terms are given by 1 divided by root of n. In this case, what function f should I be picking? F of x would be what? In the previous example, f of x was what? Was that 1 over x squared? Now f of x would be 1 over radical x. And now if I take the graph of 1 over radical x, it's a similar curve. Now in this case, notice that if I look at the interval from 1 to infinity and then I divide it into subintervals of unique length, 1 to 2, 2 to 3, and so on each subinterval now I am drawing a rectangle where height of each rectangle is the height of the curve at the left-hand point. You see that? Okay. Can someone tell me what's the area of the first rectangle? 1. What's the area of the second rectangle? What's that? 1 over radical 2. The area of the third one will be 1 over radical 3. So if you add, what's the total area of the rectangles? The total area is given by 1 plus 1 over root 2, 1 over root 3 plus 1 over root 4, right? The total area of the rectangles is given by the series that we are looking at. Notice the total area of the rectangles is obviously bigger than the area below the curve to the right of 1, right? The area below the curve to the right of 1 is definitely smaller than the total area of these rectangles, because these rectangles are the area below the curve is inside these rectangles, right? So I could say that the sum of the series that I have must be bigger than the integral from 1 to infinity of 1 over root x, right? This integral gives you the area below the curve. Now, what can you say about this integral? Is that a convergent integral? Remember, I gave you the p integral from 1 to infinity. So remember that I told you the following fact, that if I have the integral from 1 to infinity of 1 over x to the p, right? And then this is convergent if p is what? Greater than 1, and divergent if p is smaller than or equal to 1. You see, divergent means what? Divergent means, remember, this is defined to be the limit as t goes to infinity of integral from 1 to t of 1 over x to the p dx, right? Defined to be that. And it's divergent means that this limit is infinity, okay? It's as t gets bigger and bigger, the value of the integral from 1 to t is getting bigger and bigger, okay? So that tells you, in our case, that the series that we have should be divergent, because the sum of the series is bigger than this integral, but this integral is divergent, right? This integral diverges. Is that making sense to you? Everybody's okay? So what's the general test? The integral test is the following. Suppose that I have a series, sum n going from 1 to infinity of an, and an, the nth term of the series, is given by f of n, and where f is a continuous function, it is a decreasing function, and it's a positive function. F is a continuous decreasing positive function, and the nth term of the series is given by f of n. Okay? Then we could say that if the improper integral of f from 1 to infinity is convergent, then the series is convergent. If the improper integral of f from 1 to infinity is divergent, then the series is divergent as well. Okay? So whether the series is convergent or divergent can be determined by looking at whether the integral is convergent or divergent. Okay? Did that make sense? Is everybody clear on what this test is saying? We are going to see another example in a second. Everybody is clear on what this test is telling us? Okay, so let's. One thing I want to note here is that the condition here is that the function f is a continuous positive decreasing function on the interval from 1 to infinity, right? This condition here can be relaxed. That is, I don't have to start at 1. This 1 could be 2, 3, 4, whatever you want. Okay, as long as you have, if f is a continuous positive decreasing function on an interval of the form a to infinity, that's fine. It doesn't have to be 1. Am I making sense? It doesn't have to be 1. Let's look at an example. Now please raise your hand if you have questions. If you have questions, raise your hands because I'm pretty sure you have a lot of things to do now. If you are hoping to go back home and think about it and figure things out, it's probably better to ask me now. Okay. Let me give you an example. Oh, first of all, this series that I have here, the sum n going from 1 to infinity of 1 over n to the power p, this series is called a p series, okay? It's called a p series. And a p series is convergent whenever p is larger than 1. Why? Why is that the case? What happened to... Why is this p series convergent when p is greater than 1? Yes? Limit of what goes to 0? One over n to the p goes to 0. Okay, remember I really warned you about this yesterday, that just because the terms go to 0 doesn't mean that the series is convergent. Remember I warned you about that? That's a very common mistake. People would say, hey, the limit of this 1 over n to the p is 0, therefore the series is convergent. That's not how it works, because that's true also for 1 over n, right? Remember, if I have p is 1, then 1 over n goes to 0. However, 1 over n is the harmonic series that we showed last time. The harmonic series is divergent, right? So that argument wouldn't work. The reason it's convergent is because we are applying the integral test, right? By the integral test, right here. Okay, by the integral test, the series that I have here, n going from 1 to infinity of 1 over n to the p, right? This series is convergent if and only if the integral from 1 to infinity of 1 over x to the p is convergent, right? The integral test that we just looked at says that the p series converges if and only if the integral from 1 to infinity of 1 over x to the p is convergent. And we know that this integral converges when p is greater than 1, and it's divergent when p is less than or equal to 1, right? Is everybody okay with that? All right, so the integral from 1 to infinity of 1 over x to the p dx, that's convergent when p is larger than 1, and it's divergent when p is less than or equal to 1. Knowing that, we now know that the p series is convergent when p is larger than 1, and it's divergent when p is less than or equal to 1. What are we applying? We are applying the integral test. Okay. Now, here's my next example. Let's say we are given the series n going from 1 to infinity of log n divided by n, and we want to determine whether this series is convergent or divergent. And I want to show you how we could use the integral test to determine whether the series is convergent or divergent. So here in this example, we have the series n going from 1 up to infinity ln of n divided by n. In this case, if I want to apply the integral test, what function f should I be picking? What should be f of x? Well, it just replaced ln of x over x, right? Just replacing n by x, right? Now, before we apply the integral test, we have to make sure that f is a positive function, decreasing function, continuous function on an interval from a to infinity for some a. Okay? So how do we do that? Well, do we know how to determine where a function is increasing and decreasing? We know, right? How do we do that? Find the derivative, right? So what's the derivative of this guy? What's the derivative of this guy? What rule should I apply? Quotient rule, okay. Square the denominator, and then it's what? High D low, D high low, what is that? Okay. So, okay, x times what? X times 1 over x minus ln of x times derivative of the denominator is 1, right? And so what is that equal to? 1 minus ln of x divided by x squared. Okay, now in order to know where the function is decreasing, we have to know where the derivative is positive or negative, right? Now, the denominator here is always positive, right? So the sign of the derivative depends on the numerator, right? So the question is, when is the numerator negative? So f prime of x is negative if the numerator 1 minus ln of x is negative, right? Can someone tell me for what values of x is 1 minus ln of x negative? In other words, this would mean that 1 is less than what? ln of x, or ln of x is larger or equal to 1, right? So can someone tell me for what values of x is ln of x larger than 1? What's that? E, right? ln of e is 1, right? And ln function is increasing. So if ln of e is 1, then ln of x is bigger than 1 as long as x is bigger than e. So here's how the ln of x graph looks like, right? It is like this, and ln of e is 1, right? ln of e is 1. So I know that this is true if x is larger or equal to e. Everybody is okay? Sorry, why did I use greater than or equal to? I don't want that, just strict inequality, okay? So what we know then is that, so now I could say that the function f of x, which is ln of x over x, is decreasing on what interval? E to infinity, right? And it's clearly the function is continuous, clearly the function is positive, right? On this interval. So the conditions of integral test are met, okay? We can apply the integral test. So in order to apply the integral test, what do I have to do? I have to look at the integral from 1 to infinity of ln of x divided by x dx. In fact, I don't have to start the integral at 1. I could have started the integral at e, or even 3 or 4. It doesn't matter. So I have to look at this integral and say, is this integral convergent? Well, let's see. How do you? What is the value of this integral? Well, I have to take the limit as t goes to infinity, integral from 1 to t, ln of x over x dx. Can someone tell me how to evaluate the integral? U sub u is what? U is what? Say it again. Just x? ln of x, right? Very good. So this is, you're going to use u to be ln of x, and then du would be what? 1 over x dx. So I could say then 1 over x dx together becomes du, and then ln of x becomes u. So you get u du. And how does the limits change? How does the lower limit change? Lower limit becomes what? 0, and the upper limit becomes ln of t. So what do I have then? I have the limit as t goes to infinity. Integral of u is what? U squared over 2, ln of t and 0. And then I have the limit as t goes to infinity. If I plug in ln of t, I get this divided by 2. If I plug in 0, I get 0, so I wouldn't write that down. What's the limit then? What's the limit? What's the limit of ln of t as t goes to infinity? Infinity, very good. So again, why is that the case? Well, that's the graph of ln of t, right? As t goes to infinity, ln of t goes to infinity. So I have that. So the integral from 1 to infinity of ln of x over x is divergent, and by the integral test, the series n going from 1 to infinity ln of n over n is divergent, right? Because the integral test says if that integral is divergent, then the corresponding series is divergent. If it is convergent, the corresponding series is convergent. Am I making sense? Is everybody okay with that? Once again, the conditions are the function f that we have needs to be positive, right? Needs to be continuous and needs to be a decreasing function. Okay? Otherwise, we can't really use it. Any questions on what we did so far? Where is the slideshow? Okay, so that's what we were looking at. Once again, just to recap, the function f of x is ln of x over x. What we said is that this function is positive, continuous for x larger than 1, because the numerator and the denominator, they are continuous for x greater than 1. And we looked at the derivative. We said that the derivative is 1 minus ln of x over x squared. And we said that the derivative is negative when x is larger than e. So we know that the function f is a decreasing function from e to infinity. When x is bigger than e, it's decreasing. So now we can apply the test. In order to apply the test, we look at the integral from 1 to infinity of ln of x over x. That integral is infinity, so it's divergent. And because it's divergent, we can say that the sum ln of n over n is divergent as well. Is everyone okay with that? Questions? Any questions at all? Okay, so this is where I ended in the other class. So what I'm going to do now is that I am actually going to do some homework problems, and for the rest of the time, that's what I plan to do. Okay. Any questions on anything that we did so far? You should be able to do the homework problems now in section 11.3. Okay. There is another topic in this section that I am going to cover, but I won't be asking you any questions from that part. Everybody's okay with that? All right. Okay, so let's go over a few problems now from the homework. Okay, so from the homework, the couple of problems that I want to do are the following. Let's look at, first of all, section 11.2. And let's say I have the following question. Let's say I have the series, I don't remember exactly which number that I'm doing because I have a list here and I didn't write down the corresponding numbers from the exercise. So let's say I have the series n going from 1 to infinity of 2 to the power 2n multiplied by 3 to the power 1 minus n. The question is it convergent or divergent? Okay, is it convergent or divergent? Okay, is the question clear? How many of you have done this problem? Okay, so let's examine this. Anyone has any idea what I should be doing? Anyone has any idea? One thing I want to do here is that, first of all, that 2 to the power 2n, I am going to write it as 2 squared to the n. And 3 to the power 1 minus n, I'm going to write it as 3 to the 1 times 3 to the negative n. Is that okay to do? Is that okay? Everybody is okay with that algebra, okay? So now I am going to write it as n going from 1 to infinity. 2 squared is 4, so I get 4 to the n. 3 is just a constant. Remember, if I have a constant factor, I can take it outside of the sum. That was one of the properties that I gave at the end of 11.2. So I will take out the 3 outside of the sum. And then I have 3 to the negative n. Is everyone okay with that? Now, what should I do? Anyone? What should I do? Okay, so I have 4 to the n divided by 3 to the n. You guys agree with that? Okay, now what should I write? Say it again. Remember, that's not a valid algebra. But what you're saying is that if I have, say, 4 cubed divided by 3 cubed, right? You're saying, can I cancel these 3's? The answer is no. Okay, so this cannot be done. Okay, so what we could do here is write 4/3 to the n, right? 4/3 to the n. What kind of series is that? Is that a geometric series? What is R? R is 4/3. Everyone is okay with that? I don't care what A is now, because this value is larger than 1. Is this series convergent or divergent? When the common ratio is bigger than 1, the geometric series is divergent. When the common ratio is between -1 and 1, it is convergent. So this is divergent, because the common ratio, this is a geometric series, right? This is a geometric series with common ratio r bigger than 1, and we know that in that case the series is divergent. I don't care what is A in this case, because if it is divergent, there is no sum, right? And A doesn't play any role if I'm not talking about the sum. Everybody's okay with that example? All right. Here is another example. This is an example of what we call a telescoping series, okay? Telescoping series. Let's say I have the series n going from 1 to infinity, 1 over n multiplied with n plus 1. Let's say I have this series. Can someone tell me, do you expect this series to be convergent or divergent? And why? Do you think this is convergent or divergent? If you, yeah. Why? Yeah, so that the term that I have, 1 over n times n plus 1, that's almost 1 over n squared, right? And we know that that's the p series with p equals to 2, and that's convergent, right? So you expect this to be convergent. Now, if I want to, but what I want to do though here is that I want to find the exact sum of this series, okay? And we could do it in this case because it's a telescoping series. And here's why. I am going to let an to be 1 over n multiplied with n plus 1. And remember we did that partial fraction decomposition. And if I use partial fraction decomposition, I can write this as what? 1 over n minus 1 over n plus 1. Okay? I can rewrite 1 over n into n plus 1 as 1 over n minus 1 over n plus 1. You guys agree with that? Well, just add the right hand side. You'll see that that's the case, right? But you could apply partial fraction decomposition technique. It's a pretty easy example of that, right? Everybody's okay? So I can write the nth term in this way. Now what is so good about it? Well, let's note the following. What is A1? What is A1?
6 plus.
Was that A1 is what? Well, it's 1 minus a half, right? I'm not going to subtract. What is A2? Half minus a third, right? Okay. Try to see a pattern here, okay? So A3, a third minus a fourth. I'll do one more, 1/4. Will be 1/4 minus 1/5, right? Now if I continue, right, dot dot dot, can someone tell me what is an minus 1? Remember what was an? An is 1 over n minus 1 over n plus 1, right? So what is an minus 1? 1 over n minus 1 minus 1 over n, right? And the last one I'm going to write an is 1 over n minus 1 over n plus 1. Now I ask you the following question. What is Sn? Can you give me a closed form formula for Sn? What is the closed form formula for Sn? Why is that? Very good, very good. Why is that? Okay, so you are canceling half and a half, canceling third and a third. You're adding all of them, right? All of them, and then you're canceling this, and you can see that all of them will cancel out up till this point, right? This one will be canceled out with something. So what is left when you add them is 1 and n plus 1, 1 over n plus 1. So Sn is in fact 1 minus 1 over n plus 1, right? And what's the limit of this guy? Any questions? And the limit is what? 1. So we could say that the series n going from 1 up to infinity, 1 over n times n plus 1 is exactly 1.
Okay. Yeah. I'm sorry, to go back up a little bit.
Yeah.
Why is it 1 over n minus? Where's that minus coming from?
Minus what?
1 over n minus 1 over n plus 1.
Oh, the first line here?
Yeah.
Oh, you're using partial fraction decomposition to rewrite the fraction 1 over n into n plus 1 as the difference of 1 over n minus 1 over n plus 1. Just notice the following. On the right hand side here, what's the common denominator? N times n plus 1, right? And then how would you add them? Well, it will be 1 times n plus 1 minus n times 1, right? Wouldn't you get 1 in the numerator if you add them or subtract them? Is that making sense? So if you are not sure, you're applying partial fraction decomposition, right? So you know that you can write 1 over n, n plus 1. You can write it as a over n plus b over n plus 1, right? Right, instead of x and x plus 1, we have n and n plus 1. And then you can come up with the value of a and of b to be 1 and 1. So I am actually using partial fraction decomposition. But in this case, it was pretty easy to come up with a and b just by looking at it. Everybody's okay with that? All right, so that's called the telescoping series because the terms sort of are vanishing when you're taking the sum. Any questions on that example? Okay, another example. Let's say I have the series n going from 1 up to infinity. Let's say I have nth root of 2. Nth root of 2. So that's the series that I have. The question is it convergent or divergent? You'll see this question over and over again in all the sections. Is this series convergent or divergent? Okay. Anyone? Has anyone done this problem in the homework? How do I test whether this series is convergent or divergent? This is obviously not geometric, right? And so I cannot apply geometric series. It doesn't look like it's going to be telescoping either. Okay? So what else? What other tests do you have in this section? Yeah. 2 to the 1 over n, yes. And so here my nth term is 2 to the 1 over n. That's true, right? Nth root of 2 is the same as 2 to the 1 over n. But what other tests are in section 11.2 that can be used here? Remember, test for divergence. Test for divergence, what does it say? What does it say? It says that if the limit of the nth term is not 0, then the series is divergent, right? So let's look at the limit. Let's look at the limit as n goes to infinity of the nth term 2 to the 1 over n. What is this limit? What is this limit? Is this limit 0? What's that? It goes to 1, you're saying? Okay, how is that? Well, remember the trick. You can write it as e to the 1 over n ln of 2, right? 2 to the 1 over n, that's the same as e to the exponent 1 over n times ln of the base. Now, what's the limit of the exponent as n goes to infinity? Obviously what? Obviously, the limit of the exponent is 0. So you do get what you said, 1. Okay? So notice that 1 is not 0, right? Any question on that? 1 is not 0. By the test for divergence, the series n going from 1 to infinity of 2 to the 1 over n is divergent. Because it says that if the limit of the nth term is not 0, then the series must be divergent. Okay? And the mistake that somebody made at the beginning was saying that if the limit of an is 0, then the series is convergent. That's not true. If this limit was 0, you could not say that the series is convergent, okay? If this limit is not 0, you could say it's divergent. But if the limit is 0, you cannot say it's convergent. And that's the mistake that somebody made here today, okay? And again, I'm warning you, that's not true. And I'm pretty sure somebody will use it in the exam, okay? Because every year someone uses that, okay? And I'm, again, probably someone who doesn't show up. But, well, if you don't do the homeworks, it's pretty easy to make that mistake, okay? If you do the homework, you'll see that you'll be warned when you do the homeworks. Okay, I have 5 more minutes. Let's do another example. And this might be pretty... this might be a very good example to be to appear soon, right? That's how they say it. It's going to appear soon, right? So n is 1 to infinity, 1 plus 2 to the n over 4 to the n. Is it convergent or divergent? Is it convergent or divergent? If it is convergent, find the sum. Okay. So what should I do? I think I did an example like this last time. What should I do? Anyone? Split it up. 1 over 4 to the n plus 2 to the n over 4 to the n. Okay, I did that. What's next? Can I write n going from 1 to infinity, 1 over 4 to the n, 2 to the n over 4 to the n? What is that? Yeah, can I say it is the same as 1 to the n? In other words, I have basically this, right? That's what you're saying? Okay, now I can take the sum one by one. Yes. Yes, we'll do that. Yes. N is going from 1 to infinity, 1 over 4 to the n plus the sum n going from 1 to infinity, half to the n. You guys agree with that? That was one of the properties that I told you about last time. And then, well, the first one, is that a geometric series? They both are geometric series, right? What's the R value in the first one? Is 1/4. And what is the A value? What's that? 1/4, right? Remember the geometric series, the form that we are using, n going from 1 to infinity, a times r to the n minus 1, right? So the exponent on r starts at 0, right? So notice that I have the sum n going from 1 to infinity of 1/4 to the n, right? That can be rewritten as 1 over 4 times 1 over 4 to the n minus 1, right? Now it matches what I have here, right? So the A value would be 1/4. Okay? So you have to make sure the index n is starting at 1, and then the exponent on r is n minus 1. So what is A? It's 1/4. What's the R value in the second one? And A value? 1/2. So then I could now say the sum is what? What's the sum of the geometric series? It's A divided by what? 1 minus R, just R, 1 minus R. So then I'll have here 1/4 divided by 1 minus r, plus in the second one I have 1/2, 1 minus a half, right? And what's that equal to? In the denominator I have 3/4, right? Here I have a half over a half, and that's equal to what? 1/3 plus a 1, right? And this is equal to 4/3. Everybody's okay with that? You guys are doing okay with that? Questions? All right. Thank you for giving me the 10 minutes. We will stop right here.